So we had progressed to the point where we had this determinant that we had to set equal to 0. And it involves, I'll just rewrite the determinant again. So we have 2g minus L omega squared minus omega squared L minus omega squared L and g minus L omega squared. So that was my determinant that I set equal to 0. So I multiply things out, but what I end up with will be a quadratic equation in omega squared, which I think you can see directly from here. And the solution for omega squared is 2 plus or minus root 2 g over L. So I would have two eigenfrequencies, one at a lower frequency of 2 minus root 2 g over L. Let's call that omega 1 squared. And omega 2 squared is at a higher frequency, 2 plus root 2 g over L. Just like we did in working out the principal axis tensor, we could find the eigenvectors that go along with these eigenvalues. So that would imply subbing back into the original equations and finding the solution space for A1 and A2. I'm just going to write that down. So for omega 1 squared, which here what I'm doing is looking at the lower frequency component, and I have a result that A2 is root 2 A1. And so what this implies is that our pendulums oscillate in phase. So you remember the original question, which seems now a long time ago, but we have our two coupled pendula, and these pendula, their oscillations are going to be in phase with each other. For the other solution, omega 2 squared, which is the higher frequency, we end up with A2 to be minus root 2 A1. What this implies is that we have our pendula which are going to be oscillating out of phase. And if you think about normal mechanical systems that you might encounter, it's always the out of phase motion that is at the much higher frequency than the in phase motion. Getting all the masses to move together, this is always your lowest frequency mode, has these two masses moving in phase. The higher frequency mode is always out of phase. And that's exactly what we see here. So the system, what we've done is started with this very complex double pendulum. We've made some approximations along the way, got down to where we're dealing with just small amplitude motions, and we get a result that more or less conforms to what our experience would be if we were to grab one of these and induce the motion.